Okay, good morning, everybody, and welcome to the final day of our 4-day workshop. Today we have Professor Manish Shrimali from the Central University of Rajasthan. He'll be speaking to us on reservoir computing with an actual reservoir, which is a pendulum. Okay, Manish, looking forward to your talk, man.
Thank you, Ramsar, and good morning to all. And first of all, I would like to thank ICTS and this Neuroscience, Dynamics, and Data Science organizers, Professor Ramaswamy, Professor Neelima, Gupte, and Professor Amit Apte, for this wonderful organization of this online meeting, which was supposed to be in hybrid mode, but still we are enjoying that. And giving me this opportunity to discuss about our recent work on reservoir computing with a single pendulum. So with this, I would like to first acknowledge the work done by Sanendu Mandal, the research scholar at Central University of Rajasthan, who has worked out this problem, and our collaborator from IISER Mohali, Professor Sudeshna Sinha. And for financial support, I acknowledge DST for funding our proposal. So the brief overview of this talk will be, I'll just introduce the architecture, relevance, and examples of the reservoir computing. And we had a very nice introduction on day one by Sarthak. And I'll discuss about how the dynamical systems we consider as a reservoir. And then I'll come to the focus of this talk, which is the single node reservoir using the pendulum, and the scheme dynamics of the system results discussion, and as well as I'll also discuss about the experimental relation which we have done in our laboratory. And finally, I'll discuss the results in terms of the existing network reservoir cases, and I'll consider one of them to compare our results for single node, and then I'll conclude my talk. So I'll be just going through the basic idea of reservoir computing here, which we already have an introduction in this meeting. And it is basically a deep learning framework based on the recurrent neural network architecture. And it basically uses the memory capabilities and rich dynamics of the reservoir for the intelligent computation. And the idea here is that we use the dynamical system as a computing substrate, which is the physical system or device as a reservoir. And we put this into the three main components, the input connections, the reservoir, which we will be discussing, and then the output connections. And if you go back to the history or origin of the reservoir computing, it was independently proposed in two framework, the eco state network as well as the liquid state machine, which is from the theoretical neuroscience point of view. Yeah. So the relevance of this reservoir computing, especially in terms of the data processing capacity of the dynamical system, which is very important here, that we use the rich dynamics of the reservoir as a dynamical system, which multiplexes the complex input in the higher dimensional space. And this nonlinear memory effect is also convenient for our sequential task. The main advantage as compared to the traditional machine learning algorithms here is that we don't have to train the input or the reservoir layers, but the only trainable part is the output layer, and that is through the linear regression in the readout. And because of that, the lower training cost and the simplicity, it is increasingly becoming popular among physicists in last decade, and also convenient for non-expert in computer science, and there are very variety of applications from medical science and complex systems, etc. So the focus of this talk, as I mentioned, that it is a single node reservoir and also as a physical reservoir. So I will first mention about the two broad categories or type of models which people use in the reservoir computing. is one is the eco-state network, which is the abstract form of the reservoir in terms of the random network, where the state X state of the reservoir is updated with this set of equation. And here you can see that the input is given as a U, and there are some internal weights within the eco-state network, and then there are some feedback from the output layer. So all this, the input weighted and the state of the reservoir and any feedback, if any, that is taken as a 10 hyperbolic function and added to the state of the reservoir. And this is how the state is updated. So once we have the state of the reservoir updated state, which is say X, and then we know in the training part that what is the expected output Y, and with that we can work out the W out. We can optimize that through the linear regression, and once W out is known, and for any given input we can find out the output Y from this ESN. So that is the one particular model. Another the way of doing the reservoir computing is we consider the physical dynamical system as a reservoir, where the input is encoded in the dynamics of the reservoir. So I'll briefly tell you about some of the physical reservoir people have considered in the recent past are from electronic systems, where analog circuits, VLSI, membrist are used, and also in the photonic systems. And there's a nice review article by Tanaka in Neural Networks in 2019 that can be followed for details here. And people have also worked on spintronic systems, mechanical systems where flexible robots are used, biological system, as well as where cultured cells are considered as a reservoir. So now come back to the dynamical system as a reservoir. These are some of the examples where we can consider the coupled oscillators as a reservoir, or delay dynamical system as a reservoir. And with this, if I go into the general framework of the reservoir computing using the physical dynamical system, what we basically do is we encode the input information to the state of the reservoir. And once that is encoded, we allow the system to evolve and store the further states of the physical dynamical system. And that is used to find the optimal connection with the output weight. So in the readout, we train the system to optimize the output weight. So this is the three-step process. And if you look at what are the criterias to be a potential reservoir, one should have is, one of them is the high dimensionality. So why we need that is basically the input information is multiplex in the high dimensional system in order to encode the information and process. And the rich nonlinearity helps the information processing in the reservoir. And another important property is the fading memory of the reservoir. So usually we consider the network as a reservoir, and ESN is the one example of the random network. Now, when we talk about the dynamical system as a reservoir, people have considered the phase oscillator, mechanical oscillator, or chaotic oscillators as a reservoir for this kind of training and testing of specific problems. So in all these cases, the idea was to consider the network of or the large number of oscillators. So we have thought of that can we consider the single node reservoir, maybe the physical system, or even in the brain, how the single neuron collect the information, process, and give some intelligent output. So if you look at the work done on the single node physical systems or single neuron systems, there are very few examples in recent past. And all these examples, like starting from the delay feedback system, which is a Mackey glass systems, were used, uh, and the other chaotic LC circuit or recently quantum nonlinear oscillators, or the single neuron with multiple time delay feedback. In all these cases, people have considered the delay feedback. So effectively, with the delay, you are increasing the dimensionality of the system, and you are going to almost practically with the infinite dimension system. So with this, we have thought of working with the single node reservoir, and with the example of the driven pendulum. So this is the equation which we have considered, that there's the pendulum with the natural stamping also in the system, as well as there's the external force which is periodic. So I have used this sine function to get the periodic forcing to the pendulum. And if you look at the time series, in the absence of the external forcing, a system settles down to the steady state with the oscillation suppression mechanism, and because of damping. Now, if we apply the external force, which is periodic, you can see that system shows the quasi-periodic behavior. And this can be visualized in this picture, that you can see that with this kind of the periodic forcing, system shows the quasi-periodic dynamics. So the idea here is to encode the information on the single driven pendulum and process and get the desired output, as compared to the high dimensional network reservoir. So for that, we have looked at the dynamics of the driven pendulum, which shows that as we have seen that in the presence of the external periodic driving, it has a quasi-periodic dynamics. And the transient dynamics has a more non-linearity as compared to the asymptotic behavior that I'll show you in the bifurcation diagram. And to avoid the resonance, and also we have considered the driven force frequency different from the natural frequency of the system. So first, we have done some this bifurcation analysis of the system, and where you can see that in the top panel, this bifurcation is shown as a function of the amplitude of the driven force in both asymptotic as well as in the transient dynamics. And the lower panel shows this bifurcation as a function of the frequency of the periodic forcing, again in the asymptotic as well as in the transient dynamics. So you can see that you have more rich nonlinear this behavior of the system in the transient dynamics. And we propose to the study or consider the encoding of the input information in the transient dynamics of the driven pendulum. And for that, we have different ways of doing the encoding, and I will discuss that. So for the amplitude and frequency, we have considered this the range of given in the vertical red dotted line, that is considered for the parameter range considered for the reservoir. So now let's talk about how the encoding is done into the reservoir. So we can have three different choices of input encoding. One is we encode in the initial state of the dynamics, or it can be done in the amplitude or frequency of the force. So we found that the last two choices are the efficient choices, amplitude and frequency encoding, as compared to the initial state encoding, which may finally lead to this asymptotically the same state, and leading to the loss of the input information. So what we do is we consider the one-dimensional input as UT, and that is scaled to the parameter range of the encoding amplitude or frequency. So for example, if we are doing the encoding on amplitude, so it will be scaled to the f min to f max, which is the range of the amplitude considered for encoding. Or if we are doing in the frequency domain, then we consider the W1 to W2, omega 1 to omega 2 for that. So once this is scaling is done for each input data point, the reservoir dynamic state is recorded. So once the input is done, then we allow the reservoir to evolve, and we record the information for that. So after this recording for a sufficiently long time, we reset the state of the reservoir for the next input encoding. So this is how the input encoding is done. So then we store the reservoir state, and for that we consider the transient dynamic state of the reservoir, which is the driven pendulum dynamics. So for that we record this the state of the reservoir xt at a fixed sampling rate, and this S is obtained, the reservoir state S is obtained for this length from of kappa and tau, where tau is the sampling interval and N is the number of cycles used for the this recording of the reservoir state. So once it is done, so now we have classified our tasks in two categories: the non-temporal and temporal tasks. For the non-temporal tasks, this state is Si matrix, and this for the temporal tasks, what we do is we also record the weighted the previous input states with the uniform distribution of weight Wj in the range of 0 to 1, and with the finite memory M, where M is also hyperparameter for the this reservoir. So we consider this the kind of the recording in time for the temporal task. So once it is done, so now in the regression, what we do is we obtain the complete input signal in the reservoir state vector matrix, and that matrix is, say, R here with the length x1 to xl. And the dimension of this reservoir will be kappa n cross L for the non-temporal, and for temporal it will be further multiplied with the M, which is the kind of the memory of the reservoir. So now once it is done, so for a given input ut, if the output is Vt, which is known in the training time, so this V has a relation with the W, and R is the state of the reservoir. And the connection matrix, which is 1 cross kappa n dimension matrix, can be evaluated from the training data set using the regression of this Moore Penrose pseudo inverse method. So once the connection matrix W is known to us with this linear regression, so we can find out any for any given input U, we can find out the output state, and we can compare this over the target values. So this is how we do this. And now let's come to the examples. So what we have done is we have considered the two examples. One is the non-temporal task, and where we try to approximate the 7th order polynomial, which is given by this function f of x. And this you can see that it's plotted here. And now when we do the encoding, as I mentioned, that we consider the two different encodings. One is the amplitude encoding, another is frequency. So when we do this, you can see that the predicted output is very close to the target, and with the root mean square error of order of 10 to the minus 8 to minus 10 in both the cases. And for the audience, we have considered the training data set of the 500 samples. So for temporal task, we have considered the standard the attractor reconstruction of the chaotic Lorentz attractor, where we give the input the x variable of the attractor, and we obtain the Y and Z variable of the attractor through this reservoir. So if you look at again the results for this temporal task and the amplitude and frequency encoding, our results are still remarkably well with the error of 10 to the minus 3 order even in the temporal task. So now further what we have done is we have designed this the single driven pendulum experiment in the lab, where we have considered this the cylindrical bob, which is connected with two propellers on the either side, and which generates the force to make it the driven pendulum. And we have this kind of microcontroller which get the desired the force to this pendulum, and we do some kind of initial this optimization, and then we use the gyroscope sensors which are attached to the pendulum to note the data state variable through the wireless communication. So once it is done this, then we have studied this non-temporal task of this approximating the 7th order polynomial function in the frequency encoding. So we have considered the frequency encoding in our experimental results because we found that even the presence of noise, this frequency encoding performs better than the amplitude encoding. So I'll discuss that. So what we have done is, in order to check the effect of the noise, we have considered the uniform noise of the amplitude range from -0.1 to 0.01. And we have considered this both amplitude and frequency encoding for task 1 and 2. And you can see that the error marked in the red color is with the presence of noise, which still gives a robust performance. And the frequency encoding schemes works better in the presence of noise, since the noise affect the amplitude more directly, and there's no effect on the frequency encoding in that case. So this is the case. And now this we have also noticed that the temporal task has a less effect of noise. So now in order to get the general idea of whether any single node this oscillator can do the similar kind of performance, we have considered the standard Duffing oscillator, which is another force oscillator. And you can see in the top panel we have considered this the bifurcation diagram as a function of the amplitude of this the force. And we have taken the 3 different regions of this bifurcation diagram for periodic, quasi-periodic, and chaotic regions. And in the same window, we have considered the transient dynamics also. So you can see that this transient dynamics has a rich nonlinearity as compared to the asymptotic. So again, in this case also, we have compared our performance of the reservoir in asymptotic as well in the transient state, which shows that the transient state dynamics performance is better than the asymptotic state. And in the case of periodic, quasi-periodic, and chaotic, the quasi-periodic dynamics is the optimal choice for the reservoir state. Now, in order to compare our single node reservoir performance with the network reservoir, we have considered the one example of the network reservoir where we considered the large number of this Lorentz oscillator, say 100 oscillators, and then we connect them indirectly through the local decaying environment. And this is the set of equations we consider for this system. And if you look at the dynamical states of this network reservoir in the parameter space, so we have this two parameters, say epsilon coupling strength and the alpha, which is the feedback term, we have considered for the to study the dynamical states of the this network reservoir. So you can see that in the left figure, we have plotted the dynamic states, which are basically oscillatory and steady state. So there is a transition from oscillatory to steady state via this first order abrupt discontinuous transition, where the boundary is marked with the red color. And when we look at the performance of this reservoir in the this parameter space, we found that the optimal performance of the reservoir is found at the boundary, which is a transition from oscillatory to steady state. So this can be seen in this figure, where we have plotted the amplitude of the oscillator as a function of the epsilon parameter, and also shown the performance of the reservoir. So you can see that the amplitude of the oscillator goes from the normalized value 1 to 0, and there is a certain transition with this hysteresis loop, which shows that the system goes from oscillatory to steady state via the first order transition, and the performance of the reservoir was the best in the transition region. So that also shows that at the age of chaos, or at the age of transition, the reservoir performance is the best in this case. And there are many such studies in past also. So now, in order to compare the single node reservoir performance with the multi-node network reservoir, we have considered the three different tasks. The first two are the temporal tasks of the attractor reconstruction of the chaotic Rossler and Chua system, and the third one is the non-temporal task of the filtering of Mackay glass time series. So if you compare the single node and the multi-node network reservoir performance, you can see that the single node reservoir performance is still good, and in some cases even better than the network reservoir. So this is the one comparative study, but we are not claiming that single node will always be the good candidate for the reservoir, but in many tasks we can still consider, and this will definitely help in the understanding of the dynamics of the reservoir for their performance and training purpose. So with this, I would like to conclude here that a single node, this force pendulum, shows a sufficient richness in its dynamics, as we have seen, and that help us in the information processing and for intelligent computation. And instead of multiplexing the input in the state space, the temporal encoding effectively makes it act like a high-dimensional system. And the transient dynamics has a more information processing capacity than the asymptotic behavior. So that should be the key point to consider here. And another is from the single node, we have observed that the quasi-periodic regime works better than the periodic or chaotic dynamics. So with this, I thank you all for your patient listening, and I'm open for questions now.
Hi, Manish. I finally managed to log in. We lost power. Do you hear me?
Yes, yes.
Yeah, so I have a question. This will be slow because I'm on the phone. See, the thing is, you are dealing with the pendulum, right? So it actually has the whole, it's like the circle map. So it will have these periodic and quasi-periodic regimes. And then the chaotic regimes will be above that. So this is the Arnold. So are you in the Arnold-Tung's regime, or are you higher than that?
We have like it was like basically we have checked only in the three regions of this the periodic, quasi-periodic, and the chaotic of the Duffing oscillator. And in terms of your question, I don't have like a clear
Does the
answer.
duffing have anal tongues? I don't remember exactly.
Yeah.
Probably it doesn't. So it has
Yeah.
these
Yeah.
three
That,
regimes.
yes.
Yeah. And when you say quasi-periodic regime is more efficient, how do you quantify the efficiency in terms of the speed of computation?
In terms of, because this not in terms of the accuracy.
The accuracy. Okay. Yeah.
Accuracy with the target output and the predicted one.
Okay. All right. Did you try it on any real life time series? I missed that part. Any
So yeah,
real
so
life
like
data?
not that one, but we have considered this the time series generated from the driven pendulum design in the lab. So that we have used.
Okay. Oh, okay. So that is your experimental system. The
Yes.
output from that means a actual physical lab pendulum, right?
Yes. Yes.
Okay. Okay. Sarthak, you have a question? Please go ahead.
Yeah, I have a couple of questions. I guess one question I wanted to understand was in the comparison with the physical pendulum and the multi-node reservoir. Like when you're making those comparisons, how are you choosing the network size for the multi-node reservoir for the comparison?
Yeah. So yeah, it is. It cannot be the the ideal comparison, but we have compared this 100 node this particular network reservoir and the single node. So there's a 100 node this reservoir, chaotic Lorentz system, and we have given the same task to the both and then compared. So that is only one comparison with the 100 node this Lorentz reservoir.
I see. And so I guess so in the single pendulum, I'm just trying to get a feel for the numbers here. So so if I understand correctly, so you give this input and then you're generating this transients and you're taking some number of samples. So how many samples are you drawing from the transient time series?
That is like we have considered this length of this 500 data point. Yeah.
I see. And I guess I just have one more question, I guess, and then I can let other people also ask some questions, which is that in the temporal task, I had noticed that you added some random weights to the various temporal. Like, could you give some why, like, can you give some motivation, like why did you add that, or like what were they? Like, I guess I didn't see where those weights came from. Like, is this just to increase the randomness, or is there some particular reason why these weights are better, or?
It is basically you have to encode the information because you are doing on the single node. So and you need the training for the temporal task for the sufficiently long time series. So for that purpose, you are doing that. So in the high dimensional reservoir, you are.
Yeah, so I guess my question was that why is WJ chosen from a uniform distribution instead of just being one all the time?
Excuse me, sir. May I answer this?
Yeah.
Actually, it is that it's not random. This WJ is distributed over this only, right? 0 to 1, and W0 is 0 and Wn is 1, and it's uniformly distributed. It's that it is actually to achieve that fading memory. I mean, actually, these SIs are independent of each other. Like input, like for every input point, one SI is generated. Now, to achieve that memory effect, we just added this. Like previous states are connected with lesser weightages.
I see. Okay, that makes sense. I thought it was like those were randomly chosen.
No,
Okay,
no,
that
no,
makes sense. I
understood.
understand. I see.
And
Okay,
one more,
yeah.
Dr. Sarthak, one more point I want to clarify, like the previous question you asked, like in the comparison, the network we are considering there, that network size you have considered where the accuracy saturates. Actually, it has like this asymptotically increasing and not initially asymptotically increasing, then saturating somewhere. So after saturating only at that saturation region only we have considered it's around 200 or so. Well, we are comparing the result. So once the accuracy gets saturated, around that point only we have considered. So it was around 200.
I see. Okay, yeah, I mean, yeah, this is some very, very interesting results. I probably have more questions about some details that I'll probably just ask offline because they're just about the minute details.
Yeah,
sure. Sure. Well,
let someone else have. Yeah.
Hello, sir.
So, yeah, we can still take one more question, I think. Would you like to do that?
Yes, ma'am. Sir, you show that experimental result for the non-temporal task. Have you performed the same experiment for the temporal task, what you are considered for the computational purpose?
Sorry, can you repeat quickly? Yeah.
Sir, in your slide number 27, these results are corresponding to the non-temporal task with the experiment have you performed in your laboratory.
Yes.
Have you performed the same experiment for the temporal task?
No.
Why, sir? Any reason for doing only the non-temporal task with the experimental setup?
Since we have considered right now only this non-temporal, and still the work is going on, so we have not still done even the non-temporal. Also, we have found this frequency encoding performance is better, so that's what we have shown the result here.
Oh, yes, sir. Thank you.
So thank you. We'll go on to the next speaker.